to develop the idea of spatialization. Does that sound right?
Yes.
I want us to be able to visualize where specific values might occur and make it easier on ourselves to make our graphs. And that's kind of what we start to do here, because that leads us to the more complex stuff as we get to next week. Now, the only other difference between these inequalities we're going to graph today versus what we did before, when we graphed those before, a lot of you guys would shade a whole bunch of stuff to overshade. Here, what I want us to do is we're going to make it a little bit cleaner by using directional arrows, okay? It's not anything more complicated, you're just plotting something a little bit differently, and it takes a minute or two to get used to it. So, like we've done in the past, we've got two inequalities. They're in some variance of a form. In this case, they're in standard form. When they're in standard form, we know how to do cover and solve, okay? So we're going to do that twice. Also, if you happen to have two colors, it's not the world's worst idea to have a couple of colors for some of these things, because we will be looking for intercepts. We might not be able to get through all the stuff today with intercepts, but we will be looking for where the lines are, in fact, intersecting. So we'll do that a few times through here. Top equation, cover and solve. You've got a y-intercept at -2, an x-intercept at 2/3. You okay with that? So if I want to plot at 2/3, first thing I have to do is figure out where 1 is. Well, there's 1. I have to put 2/3 close by. When we plot inequalities specifically, and as we get along into this more to their feasibility regions, I want us to label our intercepts. Here is here's 2/3, comma, 0. And then I plot my y-intercept was at -2. Well, spatially I put a 1 out that far, so I put a 1 out here, and put a 2 there. I'm kind of guesstimating my scale, if you will, right? Now, between those two dots, when I connect them, is it a solid or a dotted line? Solid, and why is it solid?
Greater than or equal.
Yeah, it's got the little equal to part to it. There's my line. Ooh, we got a label, 0, -2. Did that line go through the origin?
No.
No. Boy, that makes a great test point, doesn't it? What's 0 minus 0?
0.
Is 0 smaller than 2?
Yes.
So it is true towards the origin. So instead of shading, I'm just going to draw a couple of directional arrows. The reason why I'm doing that is because it's going to become cleaner with the more graphs you put on it. You're going to be bounding a region, and the area that it's being bounded is going to be drawn out by these arrows. Okay? I do the same thing with the next inequality. Cover and solve. Y-intercept at +2, x-intercept at
-1.
+1. So y-intercept +2. So that's at 0, 2. X-intercept was at 1. When I connect those two dots, solid or dotted?
Solid.
Solid again because of the or equal to portion. That's close enough. Did that line go through the origin? No. So, should we use that as a test point?
Yes.
It's a good idea because it's easy. What's 2 times 0?
0.
What's 0 plus 0?
0.
Is 0 smaller than 2?
Yes.
So is it true or false?
True.
And we want to cover the truth. So here, notice how our boundary has been created by these arrows. The directional part of those arrows show us which way our, what we call a feasibility region is. You guys know what I mean by the word feasibility?
Possible.
Yeah, anything in that region is possible.
So then you would erase that.
You don't have to. I'm fine by leaving it as is because then it just becomes too much work. Okay. The only other thing that I want us to get in the habit to, especially for ones that are just two equations, I want to figure out where this is. And in order to figure out where that is, isn't this just a system of equations? Yes. But here's the thing. even though they have inequalities to them, when we go to solve where they run into each other, we have to disregard the inequality symbols. Just treat it like they're equal, okay? And then just solve it like you would normally. What would you do here? I'd just add it together, wouldn't you? See how fast that would be? You would eliminate y values right away. So if I just add these two together, I get 5x is 4, x is 4/5. So I know the x coordinate here would be at 4/5. Oops. Okay. And then to get the y value, what would I do with that 4/5? I'd substitute back in. So I'm going to use the second equation because I like positive values of y. It's a little bit easier here. So I have 2 times the 4/5 plus y is 2. Notice again, I'm treating it as an equal sign. I'm trying to figure out the exact spot. Whenever you're finding these things where they run into each other, even if they are inequalities, just treat it as an equal. Okay? 2 times 4/5 is 8/5. You okay with that? Now, I have to move that to the other side. I'm going to get y is 2 minus the 8/5. Well, that's an easy fraction to convert, isn't it? What would 2 be in terms of fifths? 10. Good. So what's 10/5? Subtract 8/5. 2/5. And your ordered pair here would be 2/5. Okay? And that's where those two graphs intersected. Now, what's that? Yeah. Again, not so much the reason today for worrying so much about those intersections, but this is going to be hugely important as we get further along. Anytime we've got two lines that intersect when we have these feasibility things, I want us to start thinking, how do I find those intercepts? Okay? It's not tough. We've been doing it. It's just another offshoot of it. Okay? Not too bad? It's kind of the same stuff we were doing, just doing 2 of them on 1. Oops. All right. No, that's number 1. This one. That Peyton Manning thing was hysterical. When he was being the what do you call it, the super fans, he got baptized in au jus. He comes up wearing sunglasses and a mustache. Packers suck! And it was great. It was so funny. Did you see the Brett Favre one yet? Yeah. That's really good too. The interception calendar, I was in tears when they were doing that.
When he throws the thing.
The first one's away with it. I really, really hope somebody makes the calendar of the Brett Favre interceptions. My God, I would buy one in a heartbeat and just like give it to any one of my friends that has it that are Packers. It'd just be great. It was so funny. And watching Favre do that, he was just laughing half the time. He was just chuckling. How do you keep a straight face? Anyway, back to here. You don't need to convert that second equation to standard form. Honestly, I wouldn't, because I want to practice scaling. So we do our cover and solves like we were doing before. When you're drawing these things out, guys, give yourself a little bit extra room. Make it a little bit bigger. Paper's cheap. If you run out of paper, I got plenty of scratch paper. And a whole bunch. I finally popped it. So if I do the first one, y-intercept at -3/2, x-intercept at 3. You okay with that? 3/2 is, last time I checked, is 1.5, right?
Yeah.
Those are my 2 intercepts. Solid or dotted between the 2? Solid again, because of the equal. Gee, what didn't it go through? It's kind of nice when that happens, isn't it? It is kind of a thing. What's 0 minus 0?
0.
Is 0 smaller than 3?
Yes.
Hooray! Arrow up. Okay? Everything above that line is true. Okay? The other one I'm not converting to standard form at all because I'm going to graph it in slope-intercept. I have an intercept of -4 and a slope of 3. Well, with the scaling that I've already done, I should be able to create that graph without too much of a hassle, just by adding in some other lines. So here's my 4. I know it's intercepting here, up 3 over 1. Up 3 over 1. And I'll just leave it like that for right now, just a couple of them. I'm using the same scaling that I already have there, just by walking what I've marked. Okay? To connect those dots, is it solid or dotted? It's dotted. And this is okay to have a mixture of solid and dotted lines within these systems. It happens. Okay, back to there. Did it go through the origin? No. What's 3 times 0?
0.
What's 0 minus 4?
-4.
-4. Is 0 bigger than -4?
No. Yes. Yes.
Yes.
Yes.
Yes. So here, it doesn't become all of it true until I get to about here. So I've got this region here going out. Everybody see that? Yes, sir.
Do you want us to shape that region with scale arrows or just something like that?
But you had asked that earlier, just leave it how it is. Just draw your arrows just like that, because you'll start to see your overlap. Okay? Eventually, we'll bound the region within a specific parameter, and then it'll be even cleaner. All right? Those two lines also intersected, didn't they?
Yes.
All right, well, this is a really easy one to figure out. Remember how we said we treat this as an equal? That means everywhere I see a y value, what can I put?
X value.
Remember substitution? Substitution was another one of the means by which we could solve a system of equations. It didn't happen so much with the stuff we were doing yesterday, because a lot of the stuff we've been doing the past couple of days all had coefficients. And sometimes it was more work than it was necessary to move equations around to get things by itself. But if I've got an equation in slope-intercept form or x equals something with y, I just substitute in. So I would get x minus 2 times the quantity 3x minus 4 is 3. I'm substituting in the value of y for x. Because when you have intercept, when you're trying to figure out where they intersect, that means they have to be equal to each other. Distribute out, excuse me. And we get 1. Okay? Excellent. Well, you can you mapped it. And that's why, even though sometimes you're scaling it yourself, it looks pretty darn close, but we always want to revert back to the math. All right? Because not always will your graphs be that clean. And that's where a lot of the stuff gets into play, especially when we get to the bigger problems, where if you don't scale it just right, your ordered pairs can get messed up. That's why this is such a great practice to get used to scaling it on your own. Everybody see why y is going to be -1? I throw the 1 into here, 3 minus 4 is?
-1.
Very good. And that's where this guy's at. Okay? All right. Got one more here. Got one more. Instead of just trying to figure out what it all sink in. Because usually when you write it down and draw it and do it, you get better at it. True. Yeah. Go figure, I may have done this once or twice. I've seen this once or twice. You know? Do you need paper? I got pen. I got plenty of them. I mean, it's on you there. Now, this one's kind of giving you guys it's starting to give you a specific area. When you start to see these first two parameters here, you want to figure out what does that actually mean. What are those? Quadrants. In what quadrant or quadrants are x greater than 0? 1 and 4. Good. So x is greater than 0. So your ordered pairs was x was positive. What's y here? Positive. What's okay? So we know that. So x is positive in the first and fourth. Where is y positive? First and second. Where do those two overlap right away? The first quadrant. Whenever you see this, whenever you see x is greater than 0, y is greater than 0, all you have to do is draw a first quadrant problem. That just means you're dealing with positive values of x and y. Okay? It's a dead giveaway that you're just stuck there. Okay? So I wouldn't draw the full coordinate system because you don't need it. This is what we call a first quadrant problem because it says so. All we do is this. X is positive going to the right. Y is positive moving up. And this holds true for all the first quadrant. Okay. Where do those two lines intersect? These intersect here at 0 and 0. Remember, I'm talking about where the intersection's at. All right, they intersect there. Now, what do we do with that third inequality? Yeah, we find the intercepts. Cover and solve, right? So, where's your y-intercept? 8. X? 6. So if I say 6 is about here, and then 8's got to be a little bit further, maybe about here. What do I do with those two dots? What kind? Solid line. I got to put a solid line between the two. I put a solid between the two. Did that go through the origin? No. What is 4 times 0? What's 3 times 0? What's 0 plus 0? Is 0 smaller than 24?
Yes.
So it's true moving inward. Now, Mike, this is what you were kind of getting at with the idea of maximization. We could have a constraint function, and which of these values maximize it, depending upon the constraint, you have test points to throw into the constraint, one of which will be your maximum, one of which will be your minimum. And that's where those things come into play with the linear programming style problem. And it was just, the one we were looking at was just total. It didn't have that verbiage of constraint. Or the an optimization type thing. Okay? And that's where this gets to. Yes, sir? No, because you're bounded within a specific region. This one is bounded within that first quadrant. So no matter what, even though this line would continue through, it's already telling me, hey, knucklehead, stop, because you can't go anywhere past this. That's what that looks like. Yes, sir?
So the answer to that you made is a scale, is a 3, 4, 5 right triangle scaled up by 2.
Okay. I don't know what you're getting at, but yeah, that is a 3, 4, 5 triangle, but that has nothing to do with this. Yeah, this is one of those, yeah, it happens. It happens on that. In this case here, any ordered pair that lies within that region would be a true statement for those 3 inequalities. That's what this gets at. But yeah, you're right, this would be a 3, 4, 5 triangle scaled out by with a multiplier of 2. Okay? What this gets us to be able to do eventually, guys, is let's see. We're almost on time. What we're going to wind up doing today is we're going to put together 2, 3 equations. I got a couple of them with 4, but a lot of them talk about y equals a number, x equals a number. When y equals a number, what kind of a line is it? Horizontal. We all forget which way is horizontal. Guys, horizontal lines go left to right. When you go left to right, what never changes? Y value. Okay? Y value never changes going left to right. Psst, guys, you're going to ask this question in a minute. Vertical lines, the x value never changes. That's why it's always x equals a number. So when we start graphing stuff that has specific parameters, for example, like number 48 here. Oops. Oh, I screwed it all up. Yeah, that was a good idea. When I start looking at something like this, you're immediately bounded that y has to be greater than 0. Your x values are less than or equal to 9. X plus y is 15 and y is less than x. All right, there's a lot going on there. Where is y greater than or equal to 0? What quadrants? Top 2.
Yeah, 2.
This one right away tells me it has to be here from the first quadrant, from the first constraint. Okay? So y is greater, so it's got to be going up from here. Next one says x is less than or equal to 9. Well, where's 9?
On the right side.
On the right side. So, but what I'm doing though is I'm looking ahead. I'm going to have an x-intercept also of 15, won't I? So I know that eventually, if I say 15's here, maybe I should put 9 about here. So I'll call that 9, 0. And it's everything to the left of it. Is it going to be a solid or a dotted vertical line there? Solid. Did I need to draw that line below?
No.
No. Why?
It doesn't go below.
Correct. Get that there. So far, so good. See how you're starting, you're scaling, but you're looking ahead. You're getting ahead of yourself every once in a while before you put points on paper. X and Y intercepts then of 15. I already said this is about 15-ish. And then scale it maybe about 15 here as well. That between the two would be dotted, wouldn't it? Okay. What's 0 plus 0?
0.
Is 0 smaller than 15?
Yes.
So it's moving inward. I don't worry about here because it stops at 9. Watch what happens here. If it's 9 here, what's the x-coordinate here? 9. So I know the x-coordinate at that intersection has to be 9. Well, what did that line run into? It ran into this equation. 9 plus what is 15? Okay. And the last one says y is less than x. That's the slope of what? 1, right? So as this goes through, it would be something like that. And then you can't use 0 there, can you? No. So you have to use a different order pair. Why not use 0? Is 0 less than 9?
So it's that little like, what's that?
Yeah. The only thing is that you have to figure out where this runs into. Well, remember, this means the same thing when you're substituting in y equals x, right? What are the two numbers that add up to equal 15 if they're the same number? There you go. I posted the numbers on the calendar, what ones to do. I think it was just 6 of them. Yeah, these, sorry, 45 through 50. I started 48 for you. Sorry, I lost track of time.
But at least we know.
Yeah, it's on the calendar though, guys.